So another type of problem you might see with exponential functions is something called half-life. So it's very similar to doubling time, but instead of doubling each time, it's going to become half the amount that it was before. So this is actually an example of a decay. So half-life looks at an example of a decay, whereas doubling time looks at an example of a growth. Okay, so instead of increasing in amount, in half-life we're actually decreasing in amount. So half-life looks at the amount of time it takes for a sample or population or mass, etc., to be reduced by 50%, so half the amount that it was before. In other words, it's the amount of time it takes for it to decrease by a factor of 1/2. So this is actually what's going to represent our decay ratio. So you would need to multiply by half each time to get to the next quantity. So here's an example of exponential decay looking at a half-life problem. So we have the half-life of carbon-14, which is used by archaeologists to estimate the age of relics, is 5,370 years. So that half-life means that's how long it takes for you to just have half the amount that you had previously. Okay, so it takes over 5,000 years for you to decrease the amount of carbon-14 to half the amount that it was 5,370 years before. Okay, in part A it says, determine the equation that models the mass of the carbon-14 after t years. So let's start by writing y equals a times b to the exponent x, which is our general function whenever we're looking at exponential growth or decay. And let's think about what our independent and dependent variables are. I know the independent variable is t in years, but our dependent variable, if I look through the question again, it says determine the equation that models the mass of carbon-14. So that's what I'm actually looking at as my dependent variable. The mass depends on how long, how much time has passed by in years. So I'm going to represent the mass with the letter m. So m of t, so the mass over time, is equal to, the initial mass is actually not given in this case. So what I can do is write m naught. So m naught means the initial mass, just like p naught meant the initial population. I know p naught sounds a little bit funny. Anyways, the ratio that we're looking at in this case, remember that it tells you that we are looking at a half-life. Okay? A half-life indicates that the quantity is decaying over time, which means that the ratio I'm looking at is a decay ratio of 1/2. It's going to be a half the amount that it was previously. Okay? And how long does it take for it to happen? Well, if I just put in an exponent of t, what this means is that the population is becoming half the amount every year. But is that what we're told? No, it's not. It tells us that every 5,370 years, we're going to have half the population. So, t divided by 5,370 tells me every 5,370 years, the mass decays to half the amount that it was before. So this is going to be our equation. And thankfully, I didn't cut off the equation and have to rewrite it this time. All right. So part B says, what percent of the original carbon-14 would you expect to find in a sample after 2,500 years? Now, we're told a time of 2,500 years. So this tells me t is equal to 2,500. And now before I even try to solve the problem, one of the things you can think about is whether or not you're expecting the population to be half, or lower, or higher. And because I know that only 2,500 years have passed by, I know that the mass should be more than 50%. Why do I know that? Well, I know it takes a lot longer for it to be 50%. And if this amount of time, the half-life time, hasn't been reached, then that means that the mass can't be half the amount that it used to be yet. Okay? So 2,500 is less than the amount of time it takes for it to be half the mass that it was before. So let's plug in the information we know. Also, because I'm looking at a percentage, I can do one of two things. I can assume that the mass that I had is 100%, so that's what I'm going to do in this case. So I'm looking at the mass after 2,500 years, and I'm going to write my assumption on the side. I'm going to assume that the initial population is equal to 100%, so that means I had the full quantity of the carbon-14. So I'm going to substitute in 100% for my initial mass, times 1/2 to the exponent. T is 2,500, and the denominator, which is my half-time or half-life, is 5,370. And so this gives me an answer that's going to be messy because I know I can't divide 2,500 divided by 5,370 and get a nice number. So I'm going to just do the entire process in one step. So 100 times 1/2 to the exponent, 2,500 over 5,370. Oh, my calculator doesn't like that kind of calculation, so I'm going to do it again. So 100 times 1/2 to the exponent. I'm going to put the exponent in brackets. 2,500 divided by 5,370 and bracket. So this is what the value of 2,500 divided by 5,370 is. And now if I continue the calculations, I get 72.4 as a percentage. And I know it's a percentage because I assumed the initial population was a percentage of 100. Okay? And so what this means is, therefore, about 72.4% of the carbon-14 remains after 2,500 years. And this makes sense because if the amount of time I'm looking at is more than 5,370, then this would have at least been 50% or lower. But because it hasn't even reached 1/2 time or 1/2 life period, I know that the percentage is going to be more than that. Okay? So just a quick way to check to make sure your work is done correctly.